It's our great pleasure to next have Alyson Brooks from Rutgers telling us about dwarf galaxies from distant dark matter. Go, Alyson.
Yeah, thanks. Marta gave this amazing overview of simulations, and I'm actually going to take a different approach and do a deep dive really on one sort of problem that exemplifies how hard it can be to disentangle galaxy formation in baryonic physics from the underlying dark matter model. Okay, and so that's, this is just a reminder of like, these are the types of processes I'm talking about here. You're seeing feedback exploding out of dwarf galaxies in this movie. Okay, go this way. All right, so here is a summary slide of all the problems that people have said occur in cold dark matter, particularly at small scales. And as I think many people are aware at this point, a lot of these have been shown to be resolved if you include baryonic physics. All right, and this is still, sometimes people still don't like this idea of invoking baryonic physics. So I want to actually highlight that there are a few problems here, and that particularly these first three, which are, missing satellites problem and too big to fail problem are included in here, where you don't necessarily have to invoke this messy baryonic blowout like I was just showing in that movie, but you do have to include gas. Okay, so the main point is these are problems that were highlighted back when people thought, oh, I can just run a dark matter only simulation and figure out what the gas is doing, right? And that's because there's so much more mass in dark matter than there is in baryons that people just thought you could do that. And then they came up with these problems. But the minute you start including gas, you start including a component of matter that can cool, right? Unlike dark matter. And so the minute gas can cool to the center of your halo, that changes things. And so to solve this missing satellites problem, the too big to fail problem, the minute you have your gas cooling to the center of the halo, and then you have satellites orbiting around that extra mass at the center, you get stronger tidal stripping, right? And that seems basically, if you run any hydrodynamic simulation, people are now finding they don't have a missing satellites problem, they don't have a too big to fail problem because of that. This missing dwarfs problem has also been called the too big to fail problem in the field. And so it's a mismatch between the velocity function observed in dwarf galaxies, primarily through neutral hydrogen rotation curves, not actually rotation curves, unresolved H1 mostly, compared to the maximum velocity that you would get out of a simulation. And it turns out that just has to do with modeling the gas correctly. So if you take into account the fact that H1 does not trace the maximum value of your rotation curve in dwarf galaxies, then this actually, the discrepancy between how much it doesn't trace Vmax can actually reconcile that problem as well. Okay, so you don't need necessarily messy baryonic physics in those cases, but you do need it in these cases. Okay, you have to have lots of gas blowing out of your galaxies to solve the next two. Right, so this first one here is the fact that most dwarfs do not have a stellar bulge sitting at their center. And you just gotta, like, there's no way around it. You gotta blow out low momentum gas in order to get rid of stellar bulges, right? You gotta get rid of the gas. It can't go on and form stars. And there's no way you can modify your dark matter model that I'm aware of that preferentially blows out low momentum gas, right? So that really is a good indicator that some sort of messy baryonic physics is necessary in galaxy formation. And it turns out that if that feedback is also very bursty, it may fluctuate your gravitational potential at the center of the halo, and that transforms a cuspy dark matter profile into a core with repeated bursts of star formation. Okay, so I am now, that was my summary of anneals. If you guys want to ask me about them at the end of the talk, I'm happy to do that. I'm now going to do a deep dive on the newest problem, right, which is the diversity of rotation curves problem. I threw up a couple of other problems here, which I probably won't get to talking about today. The first is the fact that there is an issue in strong lensing, galaxy strong lensing. You see more dense things than is predicted in CDM. And the reason I put this up here is because I strongly suspect the solution might be related to what I'm going to talk about in terms of diversity. And then some people say that the planes of satellites is a problem, and some people say it's not. And I'm just going to leave it at that. Okay. So diversity, in case you are unfamiliar with the idea of the diversity of rotation curves problem, this is a great summary of what it is. This is from Kyle Ullman and his collaborators as they originally defined the problem. And this is a great example here where you've got different rotation curves. So in green, These are results from the Eagle simulations. These are Kyle's simulations, and it's a bunch of dwarf galaxies that have gone into this green rotation curve. There are two other simulated galaxies here in red, and this blue curve is a real galaxy, IC 2574. And Kyle's point was, look, if you look at the outermost rotation curve, or rotation value in all of these cases, it's roughly about 70 in all of these cases. And yet, if you look at the inner rotation curve, there's quite a difference in how quickly you're hitting that 70, right? Some of these are very steep and some of these rise very slowly. And Kyle collected a whole bunch of different observed galaxies. These are not simulations, these are all real galaxies. And he plotted up, he quantified the inner value at 2 kpc versus the outermost rotation velocity and said, look, there's a huge range of diversity, and challenged simulators to try to match that diversity. And I think the NIHAO group was really the first group that responded to this. So again, here they plotted the velocity at 2 kpc versus their outermost rotation velocity. In blue, you are seeing real data from Spark and Little Things. And the gold here is the NIHAO results. And they said, yeah, we can make the slowly rising things, right? That's all these galaxies down here. But they highlighted that they can't make these, right? Which is all these ones that are circled in red. These are the steepest, the fastest rising rotation curves. And they said, actually, you know, it's like we've gone back the other way. We used to not be able to make cores. Now we can really make cores, but we can't make the steeply rising things. And this is another example of that from Roper et al. This is using, I believe, the Eagle model for galaxy simulations. And I will point out that they have redefined the inner value. So what they do is they take the outermost rotation curve divided by 35. That gives you an inner radius at which you measure the inner velocity. So really all it does is it scales with the mass of the galaxy, right? So if you're smaller, you measure a little closer in. And when they did this is a really nice example actually, where they ran these simulations and they made mock H1 data of all of these galaxies. And that's what you're seeing in red. These are a bunch of observed simulations in H1. And the squares here are the actual true underlying, right? If they just measure the mass enclosed in these simulations, that's what you would get. So the observations give you all this scatter. But also on here, these little crosses, these are real galaxies, right? And again, they said, look, there's this population of steeply rising rotation curves in these real galaxies that we don't match. And in fact, these guys took it one step further. You'll notice this HT, this is high threshold, right? So they ran these simulations with a high density threshold for star formation. And that's generally agreed that this is what gives you that fluctuating potential that makes cores. And so they ran the same galaxies with a low star formation threshold. And then they said, look, in this case, we can reproduce the steeply rising things. So it's core formation that's a problem. Okay. And so this, of course, is where a lot of people have invoked SIDM to solve this problem. So baryonic physics doesn't seem to be able to do it. And so this is a lovely result from Ren et al., where all of the data, right? So there are points on here with error bars. Those are coming from the Spark galaxies. But every line is a fit to those rotation curves, assuming that these galaxies are dominated by self-interacting dark matter, right? And so they've used a constant cross-section of 3 centimeters squared per gram. And in this case, they said basically because SIDM creates a core and it thermalizes the inner velocity distribution, and then the dark matter becomes very sensitive to what the baryons are doing. So this is actually a key result in terms of diversity. If you look at, say, this plot, if your baryons are contracted, what has happened is that means it's contracted the dark matter with it, and it's made a steeply rising rotation curve. Whereas if your baryons are very extended, then you get this slowly rising rotation curve, right? The dark matter stays in a big extended core. And so that's what these colors actually represent. They are the surface brightness of the actual galaxies that they're looking at. And so you can see there is a definite trend in terms of how quickly these rotation curves are rising. with what the baryons are doing. Okay. Okay, so I'm gonna bring it back to me for a minute, right? So I've been working hard over the last few years to develop a sample of hundreds of cosmological dwarf galaxies at high resolution. This is from the first paper that we put out with over 200 dwarf galaxies from the Marvel and the DC Justice League sample, where we actually predicted the stellar mass to halo mass relationship at dwarf scales. This, though, is the region where diversity is maximized. And, you know, thanks to CDM, I have many fewer of these than I have of these, right? They're more ultrafaints than Magellanic mass things. So if I try to put them on the diversity rotation curve plot, you know, I have a couple, but I don't have a whole lot. But there's already a tantalizing hint that maybe we have a big range. So I have spent the last year or so running many, many new Magellanic mass dwarf galaxies. And as Marta said, right, we're simulators. It'd be criminal if I didn't show you a movie while I was giving this talk. So hopefully this shows up okay on this, maybe better over there. It's over here. These are two of these new Magellanic mass dwarfs. So each one is a different galaxy, and each movie is showing you a different thing. So if you look up here, there's like purplish pink stuff in the center here. Those are the stars forming in this dwarf galaxy, and they're color coded by their age and their metallicity. And then mostly you're seeing a lot of blue gas. That's the cold neutral hydrogen gas in these simulations. You can see when feedback goes off, you might see some green and red over here. That's the hotter gas that's being heated up by that feedback. And then this one down here is a different dwarf, and I'm only showing the gas this time, and it is color coded by metallicity. And so if you watch this movie, you may have noticed it has gone from blue and is getting more and more orange. And in fact, here's like small things that are falling in. The blue is the metal pore stuff. And as this galaxy enriches with metals, it's turning more and more orange with time. I'll just let this run a little bit longer because we got a nice merger going on up here. Okay, and then I should point out too, you may notice this is actually a reasonably disky dwarf galaxy for these Magellanic mass things. Okay, so here they are. Okay, so here's my new dwarfs on the diversity plots. Got no diversity problem, and this is in CDM. Okay, so something different is coming out of these simulations than in the other simulations. Okay, and I'll talk more about that. But I want to point out, you know, these things here, these are steeply rising, but we still use this star formation density threshold that is high enough to make cores, right? So there's actually core formation happening even in these steeply rising things, but they are there, and I'll explain that here in a minute. One caveat, okay, is that I am not plotting the mass enclosed. Okay, and this is, I'm not the first person to point this out, right? When Nihao did this, they pointed out that these are dwarf galaxies, right? And the rotation velocity is being traced by the H1, which is strongly affected by this bursty star formation history. You can easily throw your dwarf out of equilibrium. And so if you use the mass enclosed, you do not get diversity, right? But the minute you instead start using the gravitational potential in the midplane, you get something that is closer to what an observer is going to measure. And that is where the diversity is really showing up. Okay, so that is one thing to keep in mind. Okay. So if I come back to, you know, comparing to this plot that Ren et al. Made and put my simulations on here that are in the same mass range, you can see that just like these real dwarfs, it actually, the rotation curves are scaling with the surface density of the stars. So these purple ones here, this is the most compact dwarf, and it is also the most steeply rising. These red ones down here are the lowest surface density of stars, and they are also the slowest rising, right? And so just like in the real galaxies, what's happening is now following the baryons, or even in CDM. And this also shows up in the sizes. I mean, maybe not surprisingly, I just said there's a relationship with surface brightness. And so you can see we get things that are very compact, but we also get things that are extended and disky. And if you come over here, the green are the older Marvel simulations, and the black are all the new Magellanic mass things that I've run. And the gray are real data, Spark, and you can see it does a nice job of matching the range of sizes. And so we think it's actually part of the reason we're getting this diversity result is that we're doing a decent job of matching the sizes of galaxies, which has not always been the case, right? So here's a plot of the half-light radius versus M star. This, I should point out, this line over here on the left-hand plot is for late-type galaxies from van der Waal. That is also over here. It's the black line. But the squares over here are Nihao, right? And so you can see Nihao tends to make very puffy things. It makes things that systematically in this mass range, 10 to the 8 to 10 to the 9, are lying above the mean relation, mean observed relation. And so that's why they're having a hard time making cuspy things, right? Or I shouldn't say cuspy things, steeply rising things is what I really mean to say, because they tend to be puffy. Now, the fun part about this is trying to figure out, why are we different than other simulations? And the fun thing is that Nihao, I always say Nihao are like our cousins, because they're run with gasoline. I run with Chang'e. Gasoline is just an older version of Chang'e. It has all the same hydrodynamics in it. I should be able to reproduce the Nihao simulations. And so this has been a fun little test. I'm going to show you a series of results for one galaxy, the same galaxy. I'm going to run it over and over again. And I'm just going to change one thing at a time. Okay, so here is our fiducial run. This is the results I've been showing you come from this. We have a star formation model that requires or follows the formation and destruction of H2 and requires that H2 is present for stars to form. It also has something called super bubble feedback from Ben Keller's models. And so here is the same galaxy where now all I've done is change the star formation prescription to what Nihao used. Okay, so they have a high density threshold. If your density is greater than 10.3 AMU per cc, and you have your gas is below 15,000 Kelvin, there's a chance that it will go on and form stars. And basically, you get the same galaxy out. So it's not the star formation that is the problem. Here's what happens when I just change the resolution. Okay, so it's this exact same thing, but now I've gone to lower resolution. The gravitational force stopping over here is about 85 parsecs. Here it's twice that, so it's about 170 parsecs. The gas resolution in these runs is about 3,000 solar masses. So over here, it's a few times 10 to the 4. This is frightening to me, what just happens if I just go to lower resolution. This is not what Nihao ran, okay? So even though I get a puffier thing here, that's not actually what Nihao ran. They used blast wave supernova feedback, which shuts off cooling for a time. So here's that exact same thing where I had just, the only change I made is the same resolution, same star formation. I went from super bubble feedback to blast wave. And man, I get a compact thing out, like a super compact thing. Right, so it's not blast wave that's doing it, okay? But this is still not what Nihao did. They had one more factor, which is they had early stellar feedback. Okay, so in order to model the UV radiation momentum injection from massive winds, they include this thermal dump from stars before the supernova even go off. And if I use that, I recover basically what Nihao gets, right? I get this big, puffy, extended, ultra diffuse galaxies. Okay, so I'm at least happy that I can reproduce what Nihao did. But if you're looking at this and you're thinking, I'm never ever going to believe simulations ever again, that is the correct conclusion to draw. Okay, it's a little frightening, but as Marta told us, right, these are numerical tools. Okay, so I wanted to tie this into SIDM a little bit. I do think that SIDM is walking a fine line, or at least the simplest case here where you've got elastic scattering. You do have to have a velocity dependent cross section. And this is a nice summary from Correa where she shows that you have to have very, very low cross sections at cluster scales. This is the range between about 1 and 10 that fixes diversity. But if you fit, this is what she did. She fit the cross section that would be required to match the densities in the Milky Way dwarf spheroidals. And what you find is that they have to have incredibly high cross sections. I know Mariangela and Oren have done the same thing. And so you really do have to have this steeply rising velocity dependence, which is fine. But what scares me is how much the ultrafaints match CDM predictions. So this is the density within the half-light radius of a bunch of Milky Way satellites as a function of their half-light radius. And that's all the colored points. And the black points on here are density profiles from CDM, from the Elvis simulation. And so basically these things are consistent with CDM. So either a CDM is right, or a very good model, I should say, or you've had core collapse in CDM. So we model this, we've run all these same galaxies with this velocity-dependent cross-section. And so here, just to remind you, this is what it looks like, what our diversity curve looks like in CDM. Here it is in SIDM. Okay, so the first thing I need to tell you is I have not ruled out CDM because I get the exact same results in SIDM, right? Sorry, I meant I haven't ruled out SIDM. And if I flip back and forth, you can actually see there's a slight difference, right? Your eye picks out that the SIDM curves have a bigger core, they're rising a little more slowly. Whether or not that's quantifiable yet, I don't know, because here's these galaxies on the same diversity plot. Really, the CDM and SIDM pairs aren't too different from each other. And so if you try to use this space to map a difference, it's not clear to me that you're ever going to find one within observational errors. But there is a result that might be promising, which is that what you're seeing here is the core size that comes out of these dwarf galaxies as a function of the half-light radius. And in CDM here, these circles, essentially the core size is usually about a kiloparsec. And that's because you're fluctuating this gravitational potential, and that's usually happening within about a kiloparsec. And so the core size is basically independent of the half-light radius. But that's not the case in SIDM. In SIDM, right, just like Manoj and Haibo would predict, if you have a lot more baryons, if they're contracted, you get a smaller core. If you have fewer baryons and they're very extended, then you end up with a bigger core. So if this can be tested, and it's not totally clear to me that it can be, if it can be tested, it would be one way to pull this out. So yeah, that actually brings me to the end. So, the main takeaway here is baryonic physics are very hard to disentangle from the underlying dark matter model. And so, there are a couple of paths forward, which is a lot more people have recently started running baryonic physics in different dark matter models, non-CDM models, which is awesome. But also, it's not clear that we understand dwarf galaxy formation in particular, even in CDM, right? I just showed you that, it's not clear that we get the sizes right. So yeah, there's still a lot of work to be done. And maybe one way around this is if we can identify a regime where baryons are negligible. But if we're using galaxies to study dark matter, I'm not totally sure where that regime is. Maybe that's something we can talk about. So I'll end there. Thanks.